I work at the Workforce for Data Science Center of Excellence. Scientific workflows is a word that gets used a lot for different, to mean different things, but in general, they are a combination of steps that involve big data, computational science, data science, cyber infrastructure, and mostly to solve problem as a combination of the application of these different topics under different conditions and infrastructure components. And I thought for this talk, I'd sort of take a little time machine and go back to 2002. For me, how it all started in a way. This was the first workflow I coded in CGI and Perl and, some scripting. And every step I had to do something. And I would be proud that I'm done. You would say next, you would go to GeneBank, you could get your sequence. Next, you would go somewhere else. And then I would be proud, and then I would get a phone call. Can you change this? And it would be another 2 weeks of work for me before they could do anything with it. So it was very frustrating. It was good because there was a lot that we could do with web, the internet. And it was one of those early applications in genomics that I think there were some discoveries out of that. This was a collaboration at Lawrence Livermore Lab under DOE funding. But it was always this, how can we make it more reusable? What I do, I don't have to throw away every time. And I would get, more programmable blocks together for these scientists that need what I'm doing. And, I could make myself useful in other forms also, rather than to reprogram. So in a way, a lot of us were pondering and others in the grid community. There was a whole global grid forum that had a workflow section to it around the same time. And this led to the scientific workflow tools, the first generation, I would refer to it as an answer to bring all these different cyber infrastructure components or grid components then in networked processes that, get saved as direct acyclic graphs, and they get executed, they get first defined and expressed in one of these tools, and then they would be converted to executable entities that gets distributed across these. And these first generation applications, in a way, a lot of it were around high performance computing and typical patterns of, stage, execute, fetch was the main pattern in a way. For job submission, data movement, resource management, fault tolerance become some of the things that we discussed a lot. And we are still talking about it as a resilience in the new world of new systems. Web and grid service integration. And the web services at the time was this WSDL, does anyone remember that? Web Service Description Language, SOAP protocol, and now REST services, I think, a lot more friendly to web applications. And then data querying and analysis was, if you're a little bit more data minded, you could also integrate with a database system and do some querying and add ontologies. And across that whole spectrum, provenance tracking and reusability actually become a very early topic around the workflow community around 2002, 2003. We're talking about how do we record the workflow because we are automating something and it needs to be reusable. There's no human component. And until then, nobody talked about reusability of what the human does or, the provenance of what the human does. And I think we are still talking about the reproducibility in science and mainly on the human component. And there were some network sensor data management. So these were like not edge computing, but there are sensors out there. We are streaming data from the sensors and in real time because our systems weren't made for real time on-demand capabilities. Supercomputers, between the supercomputers and the sensors, there's the whole spectrum that we missed. So how did we respond and interact with sensors was one of the things in workflows. And of course, later on, cloud computing become one of the infrastructure and environment components, and the services on a cloud ended up being a big part of the workflows. There's a a number of things, but there's a whole book on it from those times workflows. And when I look back, actually, they are still talking about very similar things. And what came out of this whole community effort, and it's a very tightly connected small community, workflow community, workflows ended up being integrated to support the whole computational scientific process. So to accelerate the design of experiments, and that my early wish of how can I actually make it easier for others to do, I think that's a lot more designable. And of course, we have notebooks now that also capture some of these workflows and the whole frameworks that they fit in. How can they be deployed and shared with groups of collaborators or team science efforts? And there's still, of course, the scheduling, running, monitoring, workflow execution, and we are doing many new things that are more intelligence integrated through AI and systems, and the scheduling is becoming a lot more coupled again. And then the promise is, if we do this right, later on we can make things reproducible, reusable, but also we can learn from them about science and team science itself. So it enables us to think through. So when I look at the spectrum, there is the programmability components that we still actually grapple with, and scalability that we still work on in different forms. And then there's the reproducibility, and these have their own meanings over time. What we've done was we built the Kepler workflow system out of this, and it was, to me, there's definitely a workflow system component, but it was a whole programming environment. It is still, but we don't make it available to communities of users. We still use it in some of the projects we are involved in. And you know, some of those components were related to data, some of that were related to computing, network operations, provenance, fault tolerance, and you could actually program a whole flow by dragging and dropping and parameterizing and customizing those components. And it was applied to scientific disciplines like astrophysics, nanotechnology, fusion, many others, bioinformatics, metagenomics, biomedical applications, and many more. So fast forward 10 years, this flow of workflows within the team science become, I think, an inspiration for integrating workflows also as a part of community gateways. So there was also a move from, instead of creating computing interfaces for individuals, which is still very important, also doing a long tail thinking and creating environments for communities. So instead of getting individual resources, can we get resources for communities? And through these gateways, community members can do their science through. And camera, for instance, for metagenomics was one of these early examples too. And the whole concept, and in many of the gateways still work this way, there's a data discovery. You have your data in some user environment. We refer to it as a data cart. And in that workspace, you can analyze it through workflows, or these days you can have a Jupyter Hub and analyze more interactively. So there are all kinds of ways we are doing it now. But then camera workflows were a central part of it. And when a user came into the environment, they would find workflows, run workflows, monitor and find histories of those runs, and then generate reports related to those. So they would even put then that data and the summary of the workflow, how that discovery that they're publishing in a materials, methods and materials section, and refer to the right bits. So it helped with also the reproducibility of the papers published through it. And at some point, camera became very successful to 5,000 plus group of a new area of metagenomics. And there would be more than 1,500 monthly workflow submissions. In those complex workflows, this means millions of jobs a month. And so it's become actually this giant computing consumer. And it made the community very successful, but there was definitely growing pains in terms of how can we make, first of all, groups understand what they're doing a lot better, and their computing needs a lot better, and access transparently to these diverse resources while they're incorporating naive tools And at the same time, how can we optimize across these environments that we need? At that time, we had local camera clusters, but we were using national resources. We were using cloud resources in AWS at that time, and Google Cloud. So how could we compute across them through this one gateway environment? That became a problem. At the same time, something else was happening. This is around 2010, 2011. The big data was definitely a term by then. And but data revolution, the way we refer to it with IoTs and new instruments, is happening. And in metagenomics, the effect of that was, or in metagenomics, what happened was next generation sequencing was becoming available. So data sizes for everything we do. So this was a workflow for clustering and functional annotation for metagenomic sequences. Through next generation sequencing, before next generation sequencing, we had some data size, some CPU time of execution of the workflow on those, some memory needs, and some needs for parallel computing. Some didn't need parallel computing. It was just a quick, QC, for instance. Some needed data parallel. We had Hadoop and MapReduce functionality through some of those building blocks. Suddenly, when you look at the same ones, next generation sequencing was definitely becoming a lot more data. And all these CPU memory needs were also becoming sort of more stretched through the continuum and to the levels that we didn't have it in the resources we had access to. And of course, when you think of big data back then, around 2015 now, not that even, back when, but it was still quite a limited set of tools, and higher levels of that architecture when you built one was expression and interactivity, and the lower levels was more about storage and scheduling. So these nuanced aspects of what kind of store, how do you make sure you query across them? Everyone's question was, I have a Hadoop cluster, what do I do with it? And I was like, you probably can't do much with it until you integrate it with something. But on-demand compute with big data was still kind of, everyone was trying to figure it out. And the BioKepler approach, we built these needs into a module called BioKepler at the time. And to combine bioinformatics tools that the community is building and developing on a regular basis with blocks that connect them to various computing environments. So you could actually pick either manually or automatically where that block would execute and sort of compute across that. So, and that would help us with both support for big data and cloud and national cloud environments without burdening the user of, trying to know where they need to be using that particular module. So there was some benchmarking and things like that involved to pick the right one. If you didn't have data, that block needed to be built. But overall, once built, it would help programmability of the bioinformatics workflow. And we used it in a number of different applications, for instance, for drug discovery using the Amber, at the time, GPU tool. So this was also even a problem, right? So using a GPU versus CPU, they were different clusters and some integrated ones were happening. But at least we could scale execution of the problem and solve across this infrastructure components we had. And of course, this was also about the time that we couldn't ignore what people wanted to do with notebooks anymore. Not that we were ignoring it, but we needed to find different ways of making these more HPC-oriented workflows work with the notebooks at the time, Jupyter notebooks. Now Jupyter Hub actually helps solve that problem quite a bit. So there were a lot of exploration there, I think. Do we execute workflows from the notebooks, and do we put notebooks as a set of steps within a workflow? All of these have been tried and tested. And I think we have a healthy balance there right now. So another 10 years, and today that means, I think we have this AI and science context now. Everyone's trying to figure that out. And we have a digital continuum from edge to cloud to HPC. that integrates many processing units. And it's actually really complicated for one person to be programming these anymore. So it needs to also support collaboration. Why is it complicated? Now, individual submissions become a lot simpler, of course, but I think our problems are complicated in the first place. When we talk about AI and science, we talk about, many different expertise. And if you scale that into problems of the world, from climate-related challenges to what we, for instance, experienced in the pandemic, to economic and democratic issues that we are facing, both from the social sciences and natural or STEM perspective, we have very complex problems. And of course, they are solvable, at least parts of them are solvable, or we can help through advanced computing and technology. But we also need to learn how to collaborate effectively, and workflows, I think, have a huge role in that collaboration and convergence of teams. Actually, one of the big ideas that NSF put together is growing convergence research. And an idea in that sense there is to create use-inspired solutions so that we can use computing technology, AI, whatever we'd like to integrate into the solution to solve societal scale challenges collectively. So, but are we building systems that enable that collaborative thinking, or is a part of our group, okay, now we understand how this needs to be solved, let me take it and solve it. So I think we need to think in that sense, not just workflows anymore. I refer to that as team flows. Every component needs to have an owner-enabled team thinking, and talk about accountability between team members, not just performance of each step, like we did before, or accuracy, scientific accuracy, integration components. When you talk about the team doing things and integrating, you're optimizing for a lot different things than performance in that setting. But the system should enable that, because we don't want to also lose performance while we are trying to optimize for other things. So it becomes a multi-objective optimization problem. And the second context, I think we nailed this down. We are in the age of big data and AI, but what this means when we talk about AI and science, we have data coming from instruments and many other sources. We have Internet of Things that are streaming real-time data. Edge capabilities in those are possible at times. And then when we talk about AI, we are talking about machine learning, knowledge management, bringing some automation, intelligence into it, like things like natural language processing. These days, when I say AI, I think I should also talk about conversational AI. What is its role in these workflows actually is becoming a discussion. But the idea is we could use these within and outside of modeling and simulation within a scientific workflow to both steer the science and execution of that workflow, but also to simplify parts of it so we can manage larger thinking, in terms of systems. So we can actually choose something, go, choose another thing, go. So we can iterate, but through learning from data within the scientific modeling and simulation applications. So when you look at those workflows, this is sort of the pattern. There's the big data IoT, there's AI in the middle. Often the loop, of course, continues. It's a closed loop, and there's modeling and simulation. And you look at the computing needs for those, they are generally different, or systematic needs. There's also the data needs, so the digital needs, let's refer to them. Modeling and simulation still requires more and more capacity. We are talking about exascale systems today. And when you look at the big data and AI, it's more these processing units and accelerators that we are talking about, GPUs, tensor processing units, CPUs, and all kinds of other systems like new architectures like FPGAs and edge computing. When you have data together with compute, and you can bring learnings from that data, there's a whole big data management and knowledge management component that needs to be a part of that environment thinking. So some of these, we actually did a study through a national academy, and it's called Automated Research Workflows for Accelerated Discovery. In that report, this type of evolved thinking around workflows and automation of research was nicely put together. What's, I think, really striking in there is there's some tooling thinking, of course, and some overview of it, but it's more about the workflows becoming the manager of that process, the automation, and what it needs, what the workflows need now, right? Open science, how it affects it, fairness, teamwork, what that means, and how the culture around that should evolve, the team science culture. So in that sense, the study, I think, made workflows the owner of the application in this highly complex world. And it's written from that perspective. Of course, it also talks about this continuous integration of computing, data, and AI, and the systematic needs for that. So then we can say the systems learning from that is the seamless integration of AI into workflows. So this is becoming then application integration on top of many systems. So that's the next context in that sense. We are doing it on top of systems in a very heterogeneous fashion and collaborative fashion. You know, I can work in my preferred environment with data and AI integration, but then I need to bring that together, and that composability of data, computing, and connectivity through high-end networks, programmable networks, become sort of pattern for a lot of many system workflows. I think the growing needs I list here: interoperability, both between systems and services, on-demand interactive access, dynamic scalability. I looked through some old slides to find those yesterday, and these were actually a lot more part of the discussion 20 years ago than 10 years ago. Somehow there was sort of grid to cloud to back to these concepts, actually. And performance management and composability is definitely, the open box approach is definitely becoming very prominent in the recent resilience concepts that we've been exploring as a community, of course. So then I think this is an ecosystem problem. It's truly an ecosystem, although the word is very overloaded. And we need to think of services that are running on top of systems so that they fill a purpose in this capability integration. And it needs to be dynamic. It needs to be, again, usable by groups, and also through some new optimization thinking, it needs to enhance teamwork, how groups put together these applications. When I put this into an architecture, dynamic composability is more systems, resource management, and services running on top of them. Microservices, for instance, running headless or serverless is in this thinking. And then workflow management and the data lifecycle helps groups to integrate into applications. But here I think caution is, I'm really talking about new types of workflows that we don't have right now, right? It's we can reuse some of the parts of our workflow systems and tools, but they need to optimize for these new things around scientific accuracy, reproducibility, team science, and those things need to be added. And there's the making them useful to teams, reproducibility, aspects of accuracy, privacy, explainability. As we integrate many things into workflows, I think we have a role to also enhance that and make those the resilience foundation for these user-inspired solutions, that platforms that we are building around workflows. When you put those all together, it becomes unreadable. If I were to simplify that, it becomes compute storage network, composition software, services and applications through a data management fabric, and then you program applications on top of them. And there is actually a generalized way of thinking this. There's a data layer, there's a compute layer, of course they are networked, and then there's the user-facing part of it. So the simplest way to face the user these days is the Jupyter Hub. Now you can actually integrate data and access to data and analysis through those. But I'm also talking about things like maps that the users interact with, or user-inspired solutions with a user experience sequence or logic built into it as a part of the solution. So some composable systems, Expanse at SDSC actually has a composable systems functionality. In addition to some other things like gateways and cloud bursting through Slurm, we reserve a part of Expanse as a Kubernetes pool. And the idea is that pool can be federated with other Kubernetes clusters. And like Nautilus, which is now a Pacific Research Platform, become the National Research Platform. So this is a network, highly networked, 100 gigabit disk-to-disk at times, set of CPUs and GPUs. This number grows, so I'm sure they're very inaccurate after a couple of months. And on top of cloud storage like Ceph. And this is actually highly used. It started as an experimental big data machine learning cluster for computer scientists. And now there are 600 namespaces in it. And both in training and also computing, this small capacity nodes distributed are becoming highly useful to cluster together data parallel applications. So then what we do is, for instance, for that federation, we use Admiralty for federation. We federate the Expanse's Kubernetes cluster, which Enthalpy is the name for it, with Nautilus, and create a pool that has both the high capacity GPUs in Expanse, for instance, or those supercomputing capacity nodes, together with these different processing units, including FPGAs available through the National Research Platform. And you can have different topologies to that federation. I think it's a detail, but I wanted to just mention it here because I think Admiralty is pretty interesting that way, that you can try different architectures. And then what we also tried is, can we then bring edge into this and compose edge so we can try these closed loop edge to supercomputing, at least Expanse level supercomputing applications. And Sage AI at the Edge project, led by Pete Beckman from Argonne. It's a very interesting one, funded by National Science Foundation, because it couples sensors and accelerators in these building blocks. And there is a whole training and infrastructure component off the edge that users can use the data from the sensors and the edge devices to train Neve AI codes, let's code Neve AIs, and it becomes a part of an edge code model repository. And the scheduler in Sage can enable multi-users, like a community that's using Sage, to schedule these AIs into those edge nodes. So it's a programmable edge capability, and it grows by use. That's the idea. And scheduling there, of course, has a whole different name, right? It's a scale down often from what you have. And also there are very low capacity environments, and how do you do prioritization? There are lots of challenges there. But what we were able to do is bring together through a lighter version of Kubernetes, K3s instead of K8, and deploy a Jupyter Hub across these three systems: NRP, Nautilus, Expanse, and Sage. And a user, when they now bring up their notebook, they can ask for nodes, what they want and how much memory they want and things like that, couple together a computing environment for their notebook and program across these. And that actually has been very useful in especially training to send to edge, for instance, in this case. But of course, data federation, the reason we were able to do it is we used stuff that connected all of them. But with many data systems, knowledge networks, common frameworks, because Kubernetes is not built for many namespaces. It's, in that sense, we are using it for something that it wasn't built for. Maybe we'll have our own solutions there. So, and just to wrap up and give you one more application of what we are using this in 2023 is, I'll give you the wildland fire science, which I've been working on for about 15 years in different workflows. And how it started was we noticed data for wildland fire modeling comes from different sources, and these sources were growing. To model fire behavior, you need weather data. Now it's coming from forecasts, real-time weather stations, for instance. Fire environment data. This could be cameras, moisture, and other things that are coming, like fire perimeters, if there's an active fire. And they can come from remote sensors, like satellites, overhead sensing, like drones or aircraft that are flying with specialized sensing. And then there's the landscape data on vegetation, and which becomes fuel for the fire. And nowadays, you could also, not just national databases, but there are specialized sensing like LiDAR capabilities. You can actually learn a lot more detailed, accurate information. So the Wi-Fi lab tackles this issue of how do we bring all those data sets and create fire science workflows that can then be integrated into use-inspired solutions. So the whole, in that sense, model here is there is a data and model commons. We enable both adding new data sets, but also using existing data, findability, accessibility, interoperability of those data sets in a programmatic way. Just like the Jupyter Notebook, we built an AI gateway on top of those composable systems. And then new AIs and fire science can be tried through those. And then the integrated workflows on top of them use these different data and model components across that digital continuum. And then they create insights that are useful in the context of that platform. It could be for fire response, fire mitigation, or just visualization, for instance, of different weather data or field data. And there's, of course, linking to data and models component and knowledge networks here, but the execution environment in the middle is the workflow integrated one. And provenance is definitely what we are talking about. So there is a role for both these notebook-based gateways, like the Jupyter Hub, and the workflows that optimize the integration of those things that are built and ready to go. And while we are doing this, of course, doing it on top of the existing community developed things like Pangeo or community data formats was very important. But when we put those all together in real time, what this means is for an existing fire, you need to act real time. So you can use fire models that are less accurate, but fast running, because you're learning from real-time data continuously. One of the things that you want to know is that fire perimeter, and you can integrate, simple forms of AI, more complicated forms of AI into the workflow. But here, collecting the imagery and turning that into fire perimeter, and then collecting data on fire weather and fire environment, and bringing those all together to parameterize a fire model. And as you get further learnings about what the fire is doing, adjusting that model within a loop is the approach. And of course, all kinds of computing can be used. Some are more experimental for us, like smoke detection and perimeter detection. We wouldn't do it in real time. We have actually a whole California program in each fire in California. This is being used through a fusion center that we built together with the California Office of Emergency Services. But smoke detection will never be accurate enough, for at least at the moment, for us to be using it. But that smoke detection can be actually used if we had this continuum, thinking a little bit into the future. We can think of the edge sensors detecting smoke, giving us perimeters without even streaming that fire environment data. And then that would trigger modeling of the workflows. And this whole modeling and closed loop integration can be an automated task through some more intelligence added into the context. And of course, when we think of not just one fire model, which is why we built Fire 4, but many fire models executing for the right context, for the right environment, because they have different performance issues, all these different behavior models. You can think of their computing needs. For instance, here, Fireside is pretty simple, but if you talk about Elm Fire, you need a little bit more capacity to run those at the same time. And as we move into next generation fire models, we are talking about not just response related to the fire spread behavior, but we are talking about something like this, which becomes, the 3D behavior of fire. And if you have models like that, you can actually now do an analysis of, we have a lot of vegetation. We want to use fire to remove some of it, so we decrease fire risk. So more of a mitigation context. To be able to do that, you're not just responding to fire risk because fire just happened. You're really putting risk on the ground. So you need these detailed models and many scenarios in ensembles running through these models. So decreasing that performance, increasing that performance so we can actually run many models and create plans for how the vegetation could be managed. For instance, in this context, requires high capacity again at times. And we were able to demonstrate using both Nautilus and Expanse together with cloud resources on AWS for running this type of ensembles. So it's again, the pooling of resources together with the containerization of these fire models. And of course, when we are performing the fire simulation, some optimization on that computing time and cost of that through, instead of deploying on all services on each cluster, federating over the pods that are already running, for instance, things like that become the challenges to both reduce cost and increase performance. And of course, as we add AI, there are different parts, like this type of 3D modeling will require detailed 3D understanding of vegetation. We are talking about 1 meter resolution versus 30 that we have. So we were able to build higher accuracy and detailed data sets. And that's a part of the workflow as well. And talking about the fire environment, when these burns are executed, there we go to the edge computing again, because there are some things that we need to monitor and continuously integrate into the models we have. That could be emulators at that point. We won't run the fire models maybe, but the insights learned at the edge needs to be integrated. So then the computing, the dynamic composition becomes, can I integrate what I'm getting at the edge for monitoring the fire together with an emulator that's going to give me, if I'm within the bounds, I'm not running a whole simulation, but I'm learning from what I ran, and then integrating with edge intelligence to monitor the risk during the execution of these burns. So these are all different types of workflows. And they're very heterogeneous in these needs. And I think the composable systems concept I'm trying to I was trying to make a sense of, there needs to be some mapping, and that's going to require us to understand where each component runs. And this is something made me notice while doing this talk, which we've been tackling since camera, right? The BioKepler was about that too, in a more manually integrated way. Now we are really talking about, can we build the AIs for these so the system itself is intelligent enough to make those judgment calls or help the user? So I think we are talking about the same things, but things are evolving and they are becoming a little bit more useful for the end users to make their lives better. And there are some other projects we use these approaches in neuroscience and these ring data integration for COVID, for individualized COVID alerts and detections. I left the papers there for it. So, and I don't by any means say this is easy or turnkey functionality. And there's a lot of learnings we are having. There are lots of things we cannot do while doing these. And I think those are the real challenges facing our community. But each AI integration seems to have its own flavor of needs and workflow. And I think patterns hopefully will emerge out of these. But right now, it really requires collaboration with the infrastructure and service providers and the builders of the workflows. And the data, I think we continuously are learning. Data needs to be in the thinking from day one. Data isn't just transported through the workflow. It's actually a major part of the workflow, especially when we talk about AI integration. So I think things like Globus are making it a lot more easier to integrate computing and data. And I heard about FunkX services yesterday. That's, I think, super exciting. Thank you.
So we should be good to go. So let me do a quick introduction. So yeah, thank you. Laurent Chapin is from the Advanced Photon Source at Argonne National Laboratory, joining us remotely, obviously. And he's going to talk to us about the data deluge at the Advanced Photon Source. So Laurent, go ahead, take it away.
Yeah, thank you very much. Sorry for the problems here. Apologies. Thank you to Ian and the team for inviting me at this conference. I apologize, I can't be in person today. I have a number of commitments back to back. So I'm at Argonne, not so far away from where you guys are. So what I'll do, I think you already heard yesterday from Hannah about what we're doing at the APS. So I will take a kind of a helicopter view of what we're doing and the kind of challenges that we are currently facing and we will face even more. With the volume of data and the velocity at which this data is coming at the next generation Advanced Photon Source, which is in the process of being upgraded. So let me share my pointer. Yeah, so to put it in context, the Advanced Photon Source is one of the 5 light sources funded by the Department of Energy in basic energy science, in the Office of Science. 4 of these sources are synchrotrons, so they are circular accelerators for the APS at Argonne, about 20 miles away from the city of Chicago. At SLAC, there's the SSRL facility at Brookhaven National Lab, the NSLS2 facility that has been recently built, and the Advanced Light Source at Lawrence Berkeley. So these are 4 synchrotrons, and this is complemented by another machine, X-ray free electron laser, which is at SLAC, LCLS, which is currently being upgraded. And LCLS is a slightly different beast. It's a linear accelerator that essentially produces extremely short, very intense bursts of X-rays that are being used to look at extremely fast dynamics at the atomic and molecular level. In addition to this machine, there's another synchrotron, which is at Cornell. It's called CHESS, but this is not supported by DOE. But it's another user facility in the US. So X-ray synchrotrons are quite interesting machine, and the concept is pretty simple. The realization is quite something else. I mean, typically what you do is you start with a beam of electrons. Typically, it's a thermoionic gun that generates a stream of electrons. These electrons are accelerated in a linear accelerator, and at the APS, they reach 450 MeV at this point. So this is, to put it in perspective, the rest mass of the electron is about 500 keV. So at this point, the electrons have an energy which is 1,000 times higher than their rest mass. So it's already pretty energetic particles. It's injected in a booster, and it goes around the booster synchrotron where it continues to gain energy all the way to 7 GeV in the current APS. And at this point, the electrons have accumulated in an additional, an energy that is 15 times higher than what they got in the LINAC. At this point, at 7 GeV, they reach their final energy. It's pretty high. At this point, the speed of these electrons differ from the speed of light only by a couple of parts in a billion. So that's really what we call the ultra-relativistic regime. And then they inject it into the storage ring where we gently wiggle them. You can see these wiggle lines here. So using magnetic field to accelerate them in a radial direction. And this gentle wiggle that the additional acceleration that this electron gain essentially produce X-ray light, which is actually used by experimental station that we call beamlines around the storage ring. So this is a pulse process, and as the electrons circulate around, they generate a burst of light that are being directed to these different experimental stations. Typically, the brightness of these machines are really increased substantially in the last few decades. The very first generation of synchrotrons were very intense, about 1 million times brighter than the sun. But further, so this was in the 80s. In the mid-90s, what we call third generation storage ring reach 3 orders of magnitude higher brightness compared to first and second generation sources, which is typically 1 billion times brighter than the sun. And in the last few years, we've seen the onset of new generation of synchrotrons that are yet again between 100 times and 1,000 times brighter than the third generation sources. So that puts the brightness at extremely high level. If you look at the brightness versus time, this outstrip Moore's law by a factor 3 or 4, just looking at the brightness of the source. There are also technological progresses in detector technologies and things like that that are actually making this jump in capabilities even higher than that. So typically, these machines are extremely multidisciplinary. Typically, you cut across pretty much all of the domains in the natural sciences. So you have natural science, biology, life science, earth science, environmental, chemistry, physics. A lot of studies on polymers, catalysis, and topics like that. So if you color code the experimental station that you have around the ring with these different disciplines or areas of research, you can see that a lot of these beamlines are actually capable of generating data in multiple of these different fields. The APS, to talk about APS by the numbers, it currently contain about 68 beamlines. We typically welcome about 5,500 unique users every year. Each of these unique users comes several times. Typically, in a given year, about 6,000 experiments are carried out at a facility like that. And it results in about 2,000 peer-reviewed publications per year. Quite a lot of them, about 40% in high-impact journals. And also, this kind of machine generate kind of a high societal impact as well, because they do basic research, but also deploy go into deployment and translational research. Some of the examples in the pharma industry I will show later. So that's kind of a big machine altogether. Some of the research we do, I mean, we heard, probably you heard a lot about Argonne and the battery research program at Argonne, but essentially looking at batteries in different form, looking at the chemical information in the battery, in battery grains, looking at the structural defects, the microstructure of the battery, the way that the image on the right here shows what happens at the interface between an electrode and an electrolyte, where you can do actually X-ray imaging to look at the structural aspect and the microstructural aspect of batteries. So this is an area of research that is really hot. It has been a hot topic for a long time. More and more, pretty much all of the research we do in this space is actually currently done in conditions that are very close to the real operating condition of the battery. So in situ and operando science is one of the key aspects of the work that we do nowadays. Same thing with, without going into detail, looking at catalysis. Catalysis, of course, are very important for a number of research areas. They kind of facilitate the transport of electrons. And if you look at whether it's nanoparticles or other type of catalysis, looking at the strain, the microstrain, the nanostrain of these devices, the chemical composition is absolutely important for some of the R&D at all levels, pretty much, from very basic research all the way to high TRL levels. This is something that it's a field of science very active at the APS. And in the last few years, we've seen a huge increase in the capabilities of imaging. And one of the specialty of X-ray synchrotron is to be able to investigate relatively large object with a very good spatial resolution. So if you look at the microelectronic circuits, for example, this is a 16 nanometer IC here on this image. Oops, I probably need to play the video again. You can actually image the full three-dimensional integrated circuit non-destructively, so you don't have to do it layer by layer. You put the entire object in the beam, you do tomography, like you will do a CT scan, and you can have typically 20 nanometer resolution, but with a very large field of view. So certainly the volume of data that we are able to generate with this kind of imaging technology is absolutely enormous, and it will be even more so as we enter the upgrade that I will talk about in a minute. And finally, to give you another flavor of what we do, a lot of the research we do is on protein crystallography. The APS has been a leader in structural biology. And here, the name of the game is to take a protein of interest. It can be, for example, the protein of the spike SARS-CoV-2 virus, and you crystallize it. Once you have a crystal of the protein, you put this crystal in the beam, and you use the diffraction data from this crystal to reconstruct the atomic structure of the protein of interest at the atomic level. And so this kind of protein crystallography program has a big impact in drug discovery. It has also a big impact in therapeutic in general. For example, the Paxlovid drug that was developed by Pfizer was recently for COVID-19 was done as part of one of the research program of one of the industrial beamline that we have here at the APS called the IMCA-CAT. So a lot of direct impact on society that have a direct impact on everyone's life. So we are entering a regime where we're going to jump from this third generation source capability to another, to a much brighter source. And if you look at what has happened over the last few years and what will happen in the next decade, a large number of synchrotrons are going to upgrade to this new technology that will make the beam even brighter to what it is now. So typically there are around 22 synchrotrons in the world that are planning to jump to this fourth generation technology. And the APS is very aggressive because it's using technology that will push the brightness even further than the competition. So the APS, when we are done with the upgrade next year, will be the brightest hard X-ray synchrotron in the world, and will generate, because we have 68 experimental stations, will generate a huge amount of data that needs to be analyzed pretty much in real time. So we'll talk about that in a minute. The upgrade itself, the goal is to increase the brightness by factor 500 in the hard X-ray regime. So this is at photon energies that are typically above 10 kilo-electron volt. The investment from the Department of Energy is $815 million. And we are reusing the existing large part of the infrastructure currently present at the facility. So 1.5 billion of the current infrastructure is actually reused. The program is threefold. We are investing in a completely new machine. So essentially, this is the magnetic lattice. This is an array of magnets that is steering the beam around in the storage ring. That's the central part of the upgrade program. We are investing in new experimental stations, so new beam lines that can actually exploit this new brightness and deliver it on the sample. And we're also investing in new infrastructure. For example, this what we call the long beam line building, which will host two of the future beam lines that are extremely long. They're about 250 meters away from the source of the production of X-rays. And the reason why they are so long is we can manipulate the beam optically to reach unprecedented resolution, typically a few tenths of nanometers on the sample. The upgrade of the machine in essence is the following. At the moment, the beam of electrons is going through this magnetic lattice. The red magnets here are simple dipole magnets. They essentially steer the direction of the beam by using a simple Lorentz force. And here you see another one. We have two of these magnets per cell. The other magnets are used to focus the beam. So what happened with this new generation of sources is that you pack a larger number of dipole magnets in the ring. So you have 7 dipole magnets instead of 2. So the deflection angle of each of these magnets is lower than in the present machine, and the magnetic field is lower. But you deflect the beam more often. And as you deflect it more often, between all of these red magnets, you can squeeze in, because the technology has shrunk in terms of size, you can squeeze in a larger number of focusing magnets, which enable you to avoid this spreading effect that you have with the electron beam if you don't focus that often along the circular trajectory of the electrons. And if you do that well, it means that the beam of electron, instead of being something like that, which you can see in the image here, which is essentially extremely narrow vertically, but extremely flat horizontally, is becoming much narrower horizontally. So it's essentially a round beam with a much smaller emittance than the current beam. And so the X-ray generated from this beam of electron subsequently are the much smaller angular footprint than the current X-rays. And this is where you get your brightness increase from these machines. This is a picture of how it looks like inside the facility, and if you can cut across, if you could cut across the wall here, the radiation shielding, you would see the machine underneath, which typically the new machine would look like that. So on Sunday, or on Monday of last week, we've shut down the user program to start the installation phase of this new machine. So, and on Sunday, a few days ago, we stopped the final test altogether, and now we are starting the disassembly of this machine. So we have a large warehouse outside of Argonne where the new machine is being built. So what you see here is one new sector of the new machine. We have 40 sectors like that to build and install inside a tunnel. And this is the machine that will give us and our user community the brightness increase of a factor 500. So it's quite a lot of work in terms of magnet technology, the precision, the alignment, the engineering is quite formidable. Each of these magnets is installed on this bench with a precision of about 10 micron. That's the thickness of a thin human hair to give you an idea of the kind of precision we need for these machines. And what you see on this slide is a picture of all of the beamlines, the experimental stations that will be upgraded as part of this upgrade. So the new ones are green, completely new experimental station, and the one that are upgraded, existing stations that are upgraded are in red in this picture. So it's pretty large undertaking. The shutdown is lasting for a year. And so in April 2024, we will start to commission the new machine. So what does it mean for data? Well, I just talked about the increased source brightness. So this is, typically 2 to 3 orders of magnitude increase in brightness, depends on exactly on the X-ray energy, but the factor we got is a factor 500, which is typically taken in the hard X-ray regime. We are doing more and more complex experiments. Pretty much a large number of the experimental studies that we support, they combine data from multiple samples, from multiple techniques. So you can have, for example, spectroscopy to look at the chemical speciation at the same time as you're looking at the structural information in the sample. It combines multiple facilities. Not all of the data is necessarily collected at the APS. You can combine some of the other light sources in the complex. And you can also combine other methods, for example, electron microscopy or some additional experimental data. A lot of the science we do, because the X-ray we produce are extremely energetic, we are really good at producing a large number of photons in the hard X-ray regime, which means that our beam of X-ray is extremely penetrating. A lot of the studies we do are in situ and in operando. And these studies, they require real-time feedback and autonomous control. It takes typically 6 months for a user to get beam time at a facility like that. The oversubscription is pretty high. And so if you want to really exploit your beam time in the best possible way with this operando in situ science, you want to be able to measure, understand in the physical space of interest rather than just the data space, and automatize the control so that you can tune the experiment as you go along. And on top of this, changes in the way we see the experiment being conducted, there's a lot of technological advances beyond the source itself. For example, the detectors that we use have increased dynamic range, they have faster readout rates and very large pixel arrays. So a large number of these detectors are multi-million pixel detectors. They are operating at 100 Hertz up to a kilohertz regime. And we have multiple of them, sometime on the same end station, and we have 68 end stations like that. So we really need to invest into, analyze and reconstruct massive multimodal data volumes. There's a lot of tasks involved identifying and classifying features and patterns. We have to merge simulation and experiment. I won't talk about that today, but this is essential to understand what we do. And a lot of the experiments that we are carrying out and we will be carrying out with the new machine needs to have this real-time reduction, data reduction, reconstruction, and increasingly a large number of AI and ML components in data flow and pipelines. So in terms of data, at the moment, typically the APS generate about 6 to 7 petabytes of data per year. And after the upgrade, in 2025, which will be the first year running, not yet at full capacity, and 2026 will be, we will generate several hundred of petabytes of data per year. And we do have, the 5 big V's of big data are there. The volume certainly is high. The speed at which we collect some of this data and the velocity is pretty high on some of the beamlines, and in some cases is really extraordinary. We have to ingest a large variety of data, so spectroscopy, diffraction, imaging into, and of course all of the unstructured data that goes with it. There's a lot of more and more question about error uncertainty, quantification, as in particular because we use more and more AI and ML technique to reconstruct some of the data from the detector space to the physical space of interest. So veracity is important. And of course, there's also value in the data itself because we generate huge databases that can be exploited further beyond the scope of the single experiment that we are, the individual experiment that we are doing every year. To put it in the context of the 5 light sources funded by DOE together, we will generate about 1 exabyte of data per year. I know I like this slide from Nicholas Schwartz. That's about 1.5 million movies, Netflix movies every day. And it requires about 1 exaflop of computing power for reconstruction. So that's a kind of a big data problem. Thankfully, we are at Argonne very well positioned to exploit some of the new large machines that we have on campus. So Argonne has a long tradition through the Argonne Leadership Computing Facility to provide state-of-the-art machine. We had obviously the petascale era, and recently the Polaris machine, which is about 44 petaflops, has been introduced at Argonne, and Aurora, which will be above 2 exaflop, which is currently in the final stage of installation here at Argonne. We'll see the light later this year. So in terms of synergies and being able to exploit these computing capabilities here for the light sources, it's a pretty good and very timely opportunity. So I talked about these 2 machines in the previous slide. So 44 petaflop, this is the Polaris supercomputer, and Aurora is 2 exaflop. We've been doing quite a lot of work and use Polaris as a test bed for some of the job that we will be launching later on this machine or on Aurora. We have this preemptive queuing system that enable us to essentially run some of the job coming from the APS extremely fast. And we are about 1 kilometer away from the LCF at the APS. So that means the data, the latency is not a problem. We can get data shipped across in 5 macrosec. But we're upgrading the network at the moment to reach about 1 terabits between APS and the LCF. So we use Globus for a number of tasks. And essentially, it's the entire ecosystem that is useful for us in terms of flow. Of course, there is a lot of data transfer tasks that are associated with the workflows that we have. There's a lot of compute tasks that need to be run concurrently and sometimes synchronously. And there's also, of course, a lot of searches in terms of metadata, looking at catalogs and things like that. So the Globus framework really help and facilitate, it's the glue between all of these components of the computing and data problems that we face at the facility, like the APS. So I'll give you a few examples of the things that have been done recently. So the first one is XPCS. So XPCS, sorry, the slide is a bit busy. XPCS is X-ray photocorrelation spectroscopy. In a nutshell, this is a technique where you are able to measure the dynamics of a system by doing autocorrelation in time series that you collect. So you illuminate a sample with coherent light. This system scatters, and in the far field, you collect this scatter, this pattern on a detector. And if you do that at different time interval, and you look at the correlation and the fluctuation of the intensity as a function of time, and you look at the autocorrelation between these time series, you can reconstruct the dynamical structure factor in the time domain. So it's a way to do spectroscopy in the time domain rather than in the frequency domain, which is usually associated with scattering technique where exchange of energy happens. And these data are very big. So you have a large multi-million pixel detectors detecting data at very high rates. So you have, in this case, at the APSU, at the upgrade facility, we'll have a 2 megapixel detector. You operate this at 2,000 frames per second. And this data set is absolutely enormous. So here, some of the work has been done to actually do this correlation spectroscopy using Globus. We can transfer the data to LCF. We can do the autocorrelation pretty much real time and send that to a user interface that is online so that the users can actually look at the reduced data, the analyzed data in real time. I need to mention that some of our users are actually doing the experiment remotely. This is a trend that has been going on for a few years, and this is a trend that has been accelerated by the pandemic. So having the entire workflow that connects, the data to the data reduction pipeline, and then being able to publish it online in a single integrated workflow is something that is very important for us. This is another example that has been recently worked on. This is what we call Low-A diffraction, coded aperture low diffraction technique. So typically you illuminate a sample with a beam of X-rays. This is not a monochromatic beam of X-rays, this is polychromatic. And you have grain in this sample, and you want to understand the composition of the grain, but also the strain and the stress inside the sample, which is relevant to a number of interesting problems in multiple spaces. So you want to essentially have three-dimensional information about the strain in this sample. And in order to have, in particular, the information about the depth information, so the beam, the illumination beam intersect multiple grains along the depth of the sample. So in order to have enough information to reconstruct the depth profile, you can use this coded aperture, which essentially affect the way the signal is going to the detectors. And if you scan the coded aperture with a known pattern on it, you can actually reconstruct this depth profile. This generates a huge amount of data, these kind of techniques. It has to be extremely fast. And so recently, for example, the team has been using 50 nodes of the Polaris supercomputer that I've shown before. That's about 4 petaflop of operation of computing power during the beam time. And they use GPU to accelerate the reconstruction of this data set. And so Globus here is used really in a number of different ways, certainly to launch all of the computing tasks that are being used here, but also to look at metadata into in the scan to understand the position of the scan, of the coded aperture, and things like that. A lot of this new technique are being used in such a way that the motion of this coded aperture, for example, is not deterministic. You have to solve the position of this coded aperture in self-consistently as part of your analysis chain. So the integration of understanding the metadata, doing all of this self-consistently and presenting the result, which is essentially this multi-grain analysis that we see here, to the end users is absolutely important for the future of techniques like that. These kind of techniques will be going from the micron scale to the nanoscale once we go to the upgrade the APS. So it will be even more data, larger amount of information, and the speed will continue to increase as with the brightness of the source and the improvement in detector technology. And another example is that will be really transformed. So the type of measurement that will be transformed after the upgrade is what we call coherent diffraction imaging. So in coherent diffraction imaging, you illuminate a sample with a coherent beam of X-ray. It impinges on the sample scatters, and you collect the scattering pattern in the far field. And this pattern and the illumination, if you know the illumination probe, this pattern can be reconstructed in real space by essentially algorithms that are iterative algorithms conventionally, at least, that will reconstruct at the same time the sample in the real space, which is the information you want. And the information you get is proportional to the electronic density in the sample, but also it will reconstruct self-consistently also the probe function, which is the structure of the beam that you have in the first place. This is kind of kind of heavy in terms of computing. These detectors are large. The number of images that we acquire are very large for a single experiment. And these coherent diffraction imaging techniques really exist in different modalities. You can do that in transmission, like here. You can do that whilst you move the sample. so that you have a very large extended field of view rather than a single point. So it's called tachography. You can use that in reflective geometry to have access of, for example, to the nanoscale strain in a flat sample. And so this is really a game changer for a lot of the experimental measurements that we do and we will do at the upgrade the APS. So here, this kind of technique is very, very heavy on the computing. And once again, you need to reconstruct what's happening in the sample in real time. That's the goal. And you have to reconstruct self-consistently the sample itself, but also the probe, because the beam has, fluctuation that you need to reconstruct at every point in the scan. So this is another example of how, Globus is being used as the glue that connects, the data, the experiment, some of the technique that we do at the edge. Some of the computing is done at the edge. Some of the computing is done on the large-scale machine like Polaris and Aurora in the future. There's a lot of transfer, and there's a need as well to display the information live to the user community, whether they are coming in person for the experiment or whether they are remotely connected to the APS. So that's another area that is quite interesting. We heard from the previous speaker about the kind of continuum that we see nowadays. It's not a single computing machine that is involved in all of these tasks. This is an example of this tachography scan here, where we use real-time learning and edge inference to enlarge machine to actually reconstruct the data live. So if I can start the next video here, essentially you scan the sample of interest with your X-ray beam. If the beam is focused on different points, you scan it, you obtain images. These images are reconstructed by using iterative methods to reconstruct the data. Once you have the initial data and you reconstruct the data, you can use that as a training for the HPC. And big computers are used here for the training. This train model is actually sent back to an edge device. And now that as you collect data, as you get more and more information about this specific sample, and you do this real-time AI, you actually can now do all of the inference at the edge and reconstruct the data, the sample live. So you can see here, this is a pattern that we use for some of these imaging techniques. These kind of techniques are now 3D, so you can also rotate the sample and you obtain huge volumetric scan, a little bit like a CT scan, but really at the nanoscale with billions of voxels. And so this is a big challenge to be able to do that in real time, but indeed a need to do that in real time. And you don't have to do that locally. So this is an experiment that was done transferring data from SLAC to Argonne. So some of the data collection is done at SLAC. They use edge computer there, but then they send the information, the training data, to the supercomputer at Argonne. You get back train model that you send back, and then edge computer to actually reduce the data and transform into the physical space of interest. So this neural network, for example, training model is delocalized in space. You can certainly do part of the compute problem here and part of the and the HPC on this side, and pretty much do all of this data reduction live. We will see also, I don't have yet an example of that, but we will see a huge increase in throughput for some of the technique, for example, protein crystallography. So I said previously that this is a field of science where we have a huge impact. You can see on the right-hand side here some of the recent protein structures. I think it was published in 2020 when you see the receptor binding domain of the spike protein of SARS-CoV-2, which is in green here, which is binded to the nanobodies, some of the nanobodies that were tested here. You can see the binding site, and you can see the interaction between the spike protein and the nanobodies. So we do that day in, day out. Typically on some of the beamlines, we do maybe a few hundred samples every day on a single experimental station. But in the future, we're going to do that at even faster scale. So there are now techniques which are coming from free electron, X-ray free electron lasers, where you can actually deposit a solution with a large number of nanocrystals into this silicon nitride plate. This plate has been lithographically etched and so that it contains very narrow funnels where these nanocrystals are being trapped. And typically a plate like that can trap about 25,000 crystals. This plate is then put in the beam and you raster scan the plate until you hit these funnels and you hit a crystal. Each of these crystals are all the same, but they are presented to the beam in slightly different orientation, which means that each of the data collection that you will be able to do with a single crystal is not going to be complete. So you need to get multiple hits to reconstruct the data and have enough diversity of information to reconstruct the full atomic structure of the protein. Frankly, these techniques it has been demonstrated that with current generation of sources, you can do about 100,000 hits per hour. With the upgraded APS, in principle, we can do this sort of things 500 times faster than what we are now. So you can imagine the amount of data that you will be able to generate. I mean, it's not just the data problem and the reconstruction of the atomic scale protein. As you know, in structural biology, a lot of these actually high throughput experiments are going straight into public databases, which are used for other things in other initiatives that are using large databases to understand, for example, the heat of a particular molecule against a protein of interest. So this is something that we will see more and more of also in the future. So typically, I hope I convince you that big data problem is very real at the APS right now. It's really very real at existing light sources, and it will be even more real for the next generation of light sources like the APS upgrade. We will generate about several hundreds of petabytes of data per year after the upgrade. A lot of this data is complex, it's multimodal, it supports operando science, which is becoming the norm, which means that it needs to be analyzed pretty much in real time. With more and more exploiting the full computing continuum, which means that the integration and the workflows with Globus is even more important than in the past. That includes learning from real-time data, which is certainly something that is also becoming slowly the norm. Delivering real-time analysis at scale is critical, and it will definitely provide a competitive advantage if we are successful in this mission. The access and the scarcity of the synchrotron X-ray light is such that in order to fully exploit this machine, we need to be able to do this science extremely fast, and make sure that the users have a competitive advantage by essentially doing all of experiment live. There are many other opportunities that I didn't talk about, which will also connect where Globus has an opportunity to be the glue between all of these computing tasks and data transfer and public databases and metadata searches. For example, accelerator control and fault detection is becoming a topic of interest. These machines are extremely complicated. You have thousands of parameters to control. The electron beam typically fluctuates only by, I would say, 10% of the size of the beam itself. Given that the size of the beam is about 10 microns, that gives you an understanding of how precise this machine needs to be tuned. And so accelerator control, fault detection, all these kind of things is really becoming also a big subject of interest. And so connecting, it's not so much the science, but the control of the machine itself is becoming an interesting topic in its own right. The one thing I didn't talk about, but is certainly important, is the coupling of simulations with all of this data. For example, when we do spectroscopy, we rely, to understand the data in spectroscopy, we rely on multi-electron physics, simulation, quantum chemistry calculation. There are huge progress in terms of surrogate models, accelerating some of the simulation. And certainly the integration with experimental science is a hot topic. So very much hope that Globus can play a role as well in integrating this different piece of the puzzle that we need to control in order to generate science at the end. I'll stop here and very happy to take questions.
Great, thank you. First speaker is Brock Palin from the University of Michigan. He's the Director of Advanced Research Computing at the University of Michigan, and he's going to talk about a tool for leveraging cold storage archives.
Okay, so this is really a tool that came about from scratching an itch. But basically, it's an all-in-one archive tool. There's 3 primary commands. There's a singularity container, and it's out on GitHub if you want it. But what's really going on here? So we sell storage. Lots of people sell storage. Lots of people buy storage. And of course, you sell it by the byte, but then people get annoyed when you use a cold storage thing that really cares about IOPS, right? You're talking about tape archives, we're talking about Glacier, we're talking about other things like that. And so you have things that are based on space used, which you're always looking at budget, how much for storing a petabyte, how much for storing a certain amount. But then you're worried about, you end up having to use the high performance storage system because you've got issues around file counts, the things that humans want to deal with, lots of organizing stuff. So you got the classic 80-20 rule. Most data, and I've looked at a lot of different use cases in our environment, we get hung up about leveraging archives that don't want to deal with lots of little files because of the last 20% of our data that uses a very small amount of space, but is like 80% of the inodes used on a system. And of course, it'd be like, hey, just zip it up, tar it up. Well, the problem with that is how do you do that with like many terabytes of storage? You don't want to have like a 10 terabyte tarball. I mean, you can do that, but it's a pain, right? You'd much rather have like, 10, 1 terabyte tarballs. So actually what this tool does, this is the entire workflow right here. It optionally, a lot of these features are optional. Sort your data into files over a certain size and under a certain size. If it's under that threshold, it builds lists of files. By default, it's 100 gigs each. Fires those off in a pool of thread workers. So this all happens in parallel. Everything's done in parallel. Walking the file system's done in parallel using MPI file utils. It uses a Python thread pool for creating a whole bunch of tars in parallel. And if you've got the parallel compressors like PIGs, LBZ2, and all of those installed and you use compression, it uses those also. So this flow here using gzip compression on an old Skylake node with 36 cores gives you about 1 gigabyte per second of compressed gzip. If you're not using gzip, you can go a lot faster as long as your file system and network can keep up. But effectively, the files that are over the threshold, hey, the archive, this will already stream to tape, or this will, I won't worry about, Glacier egress charges based on number of objects. Just submit those to Globus as a transfer and it just goes automatically. So I don't have to do the transfer, it's already built in. It calls the SDK, you use the API and it just fires it off. As those individual tars are created, it fires those off as their own task. So basically you're pipelining tar, compression, and transfer all simultaneously, which is quite nice. And you can do this again, all in one thing. Oh, and the most annoying thing about, man, I tarred it up and I stuck into the tape archive and I don't remember if that file's in there. It automatically uploads a little text file index so you can grep that rather than having to pull the whole thing back. Kind of like things you just learn over time. It just automatically does that for you. So here's the most basic version. You just run archive tar prefix and you can run dry run and it will just give you a histogram of the type of files you have, how much total data you have, and it'll just quit. It won't do anything. There is a way to run that where you can save the list that it gets so you don't have to spend your 20 minutes scanning your 6 million file system again. It'll just use that list when you actually want to do it. So everything here is a dry run so you can see what it does before you do it. If I want to make 200 megabyte compressed with BZ2 tars and include a purge list, what's a purge list? That's basically the little files that got stuck into tars. So you can pass that to another command called archive purge so you can delete the stuff that's been tarred, but not the stuff that wasn't tarred. So you can do that there, purge small files, check the outcome, and then you can run unarchived tar. Unarchived tar is really just a stupid parallel hack around running tar in reverse. Doesn't do anything fancy, but I've actually used it for things that weren't compressed with this. But since it's still standard tar, all your stuff's portable, right? It can go anywhere. You don't need this installed to be able to unarchive stuff. Here's an example of using Globus. So of course you can specify source and destination collections and you specify a directory on the target collection, and that's the directory it's going to go into. The source and destinations can all be set by environment variables because on most systems it's like, hey, the source is the system I'm running on, duh. And the destination is probably your archive if you have an institutional archive. So you don't actually have to specify those. We use LMOD in our environment, like probably almost everybody here uses. we just set the environment variables for the defaults in there. So in our system to archive, all you say is archive tar, prefix, destination dir, that's it. And it will, everything else has same defaults, and it will end up in your archive with just running one single command. So create tars of, so this is basically walking through what happens. So size 100 meg, basically we're saying, hey, anything over 100 meg, cold storage, it'll take that just fine. So just submit that as one big transfer. Make my target tars 1 gig. This defaults to 100 gig. This is meant to be an example that's fast, and I just, pasted it into this presentation. Compress with LZ4. If you're not familiar with LZ4, it's so fast, it basically is a no overhead compression algorithm. But if you're uploading to a file system that already compresses, don't bother with compression, but some people like it. Whoops, I opened something. Prefix, prefix is the only required option in this whole thing, and all that does is it makes my archive-1.tar, my archive-2.tar, that's all that means. It's the name of the resulting tar files. And then of course, that's the Globus part. So what could we potentially do with this thing in the future? Okay, so there's the GitHub. There's some examples of usage for doing like backups and other things that was never designed to do, but you can kind of make it do it. And there's like a collection of archiving notes that I've made publicly accessible. Okay, so I'm making many, I'm using this as a pitch for features. We're making many single large file tasks. Can I send a striped transfer hint as a transfer thing? Because I know the size of those tars, because I know what it is. And I'm putting literally one file in a transfer, because I'm submitting many transfers, right? There's one for the big files, and there's one per tar after that to pipeline the options. Should some of this be refactored into a flow? So like actually make the tar part, fire it off into individual jobs and stuff like that. It's an idea. This was all done before that. Yep, so that's it. That's it. So yeah, in our environment, you can do 3-line archive.
Excellent. He brings it in on time, so you can get a question. Any questions? Quick question for Brock. Oh, quick.
So you've got these tar files, and you were going to retrieve that list to look for stuff. But is there any plans to build like a byte offset read, so you could just pull back that slice and kind of index it?
No, I mean our archive use case has primarily been write once, read never.
Oh, yeah, I got it.
So
and I got the dashboards to prove it. So this has mostly just been a, man, this scares me. You're telling me you got all these requirements to be able to use tape. Our archives tape, but this would work with anything that has these sorts of characteristics, right? The low cost per byte, but really expensive per IOP, right? Like what's 1 seek per second on a tape robot costs? Probably like, I don't know, $20 million or something, right? To be able to have that many tape drives to average 1 seek per second. But the cost per byte is really good. So it's like, what are you optimizing for? But no, I mean, it's an interesting idea. I mean, there's interesting ideas too, like the indexes. Could those be slurped into some sort of other thing, so you kind of have a single pane of glass, so you don't look at your tars in your archive as a starfish feature request, to be able to find stuff, even though this is the way it behaved, right? This is the way it sits on media, but not necessarily how to access it. No, it's just a wrapper around a lot of existing stuff. But a lot of times we tell users like, well, you got to do this and you got to do this and you got to do that. And they're like, I'm not going to do that. I've got 3 years to finish my master's and get out of here. So yeah, right. So it's like, okay, the archive's free, CD to a directory, run module load archive tar, prefix, and a folder on the archive, and walk away. It's done. So that's been very popular, especially with life science people. And the size option, actually, we thought that was going to be used a ton. Nah, a lot of people don't use it. They leave that off. So they end up with tar 1, tar 2, tar 3, tar 4, tar 5. No big files left in place. Yes, that saves like 90% of the time. But they just like the simple, just goes and it looks crisp and clean, right? Because you just have a folder full of tars rather than folders with big files. And then you have these tars you have to overlay with little files, and they just like it that way. But there's a bunch of optional features. It was designed so that if you wanted to run it in a batch system, you could. So once it's handed off everything to Globus, it quits. It doesn't wait for the transfers to finish. Some people didn't like that because some people were started using this to do what I call a ninja backup of like Synologies under desks and stuff like that. So they wanted it to wait before they ran it because they were like looping over a bunch of different things. So we added options for wait where it pulls the API to wait for transfers to finish. And if the transfers fail, it sets an appropriate return code so you can capture that and, you know, script around it and do all sorts of other things that, again, it was never intended to do. But hey, you know, it's kind of become a little bit of a Swiss Army knife for doing all sorts of different things to just get data into low cost per byte. The remaining issue we have is actually identifying the stuff to get rid of. And we've done some stuff with Goofy. We're talking to Starfish. You know, this is a issue of how do we identify the junk in the junk drawer from the stuff that's actually being used? You know, it's a common issue. Because yeah, I mean, our data volume grew by 100% last year. So everyone was asking questions about this cost, and this has been one of the ways out. Okay, but now I think I've gone over time. Yeah.
Thanks, Brock. Okay, Sylvia, all yours. Hang on just a second. Let me give you a brief introduction here. So Sylvia Ramos is the Senior Research Software Engineer at the Rosalind Franklin Institute, and she's going to talk a little bit about what they've done with Globus.
So yeah, good morning. So I'm a research software engineer at Rosalind Franklin Institute, which is an institute in the South Oxfordshire. So this is a brand new building. It has opened in September 2021, and I started there in mid-October 2021. So, and I will be talking of how we use Globus as a key component for our research data lifecycle. So just a small introduction about what we do. So the idea is to image and interpret, and also intervene. That's the three keywords. So we work on with life sciences or biologists. So, and the idea is to look at the scale from the organ, tissue, and cell. So the image is mainly related to electron microscope. You use cryo-EM, PFIP, ptychography. You have at the moment already 5 electron microscope in production. Being used. The interpret will be more on the artificial intelligence. So I'm part of this team, so artificial intelligence and informatics team. And then the intervene is more related to chemistry. So here, what is new compared with what I used to work at Diamond Like Source is here, this is small labs with it. We have many desktop that has individual instrument and techniques. So it's quite different from what we used to see in the user facilities. So this is a busy diagram. So this is a research data lifecycle simplified. So here, first of all, so is just having an overview of about user journey. So mainly a researcher journey. So Rosalind Franklin Institute is not a user facility. So we are a research institute. And the idea is to collaborate with industry like Thermo Fisher, Waters, Bruker, and work with them to build new techniques and instruments. And then we deliver this to user facilities. That's the idea around the Franklin. As such, we don't have a user management system as a facility. So for permissions and knowing who should access the data, it was where we didn't really know at the start how to do this. Then we work with the operation team, and it's all about grants and projects. And the idea is to use WorkTribe, which is a grant management system, in order to know, to divide between project team, and then get this information and then populate the Globus groups and our LDAP. That will be the idea. So then this is the initial about plan and design. So we can extract some information from work tribe like abstracts and user reports in order to enrich our metadata catalog and our databases. So then we have the collect and capture, which is we don't have on-site data acquisition. We don't develop data acquisition software. We rely on the vendor software. So it can sometimes be challenging because we don't have proper APIs. So many use Windows, so Windows desktops. And well, so here we don't have at the Rosalind any infrastructure as such. We just have a desktop. We don't have network attached storage. We don't have any of this. So what we use is a Ceph FES and Ceph object store at SCFC, which is a building just in front of the Rosalind Franklin Institute. So this comes with some challenge, and the idea was to use Globus to transfer all this data to the building that is just in front of the Rosalind. So this has been successful. So at the moment you have 25 instruments, 21 when I wrote the abstract. Now we have 25, 26 instruments running Globus Connect Personal. We have in our backlog for the next few weeks more 3 or 4. So I've been quite a busy, less than a year schedule, yeah. So then we have the collaborate and analyze. So in here, so this is mainly, we process our data on our OpenStack, which is again located at SCFC. But we also have some agreement with Baskerville, which is an HPC system located at the University of Birmingham. So SciCat is our metadata catalog. So the idea is when you transfer the data to the storage, the idea is to use the flows to know which files have been transferred and then extract the metadata from the file and add it to SciCat. We can also add more metadata from work tribe as well, like permissions and information of proposal, about reports, everything that is related. So the advantage of work tribe as well. So by doing this, we are trying to use project codes that give us like uniformize and trying to link with our finance system. So we have idea about budget, link to the data. So it's a way that we have to link our data using these codes. So we also started to use flows with Funkex to start processing data on Baskerville, for example. So challenges that we are having is, well, usual about firewall. So we are working with them in order to open the AMQPS port. So yeah, then we have the store and preserve, which is for now mainly object store. Ceph is used at Scratch, and we use Globus to transfer data between systems. The share and publish. So the idea is to use DOIs, and but this will be future work. And then what I was quite surprised is that we can see already researchers using Globus to transfer data to Empire, which is a data repository quite well known in the electron microscope world. So finally, this is just an overview what we plan to do. So here we have the storage, that's the architecture. We have our PC, that's a different store. We plan to have some tape archive at some point. Globus is in the middle, linking everything basically. We are planning to use Kubernetes. With the metadata catalog, Airflow, Keycloak, and our virtual machine on OpenStack can be accessed through Guacamole, and use Globus to transfer data between the object store and Ceph. And yeah, that's about the acknowledgement. So you see, we're quite a small team. We are not quite, so we are 4 or 5 people working on this. And I would like to especially acknowledge Nayaz and Matthew Selbit. We saw all this Globus Connect personal across all this desktop. And yeah, so thank you for your attention.
Thank you. Thanks, Celia. And I just wanted to say RFI is a recent subscriber. So this is like all this happened within pretty much the last year. So they jumped in with both feet. So if you have questions for her, find her at lunch. Great. Up next is David Deepwell. David is the software developer at the University of Calgary, and he's going to talk a little bit about automated data sharing of medical images.
Thank you very much. So a multi-year long longitudinal collaborative study at the University of Calgary requires the collection, curation, archival, and sharing of medical images across academic institutions in Canada. This presentation will discuss the workflow that was built to automate the sharing and archiving, and the sharing between the different institutional sites is so that we can utilize the expertise of these different sites for this large-scale project. So the data, which are the medical images, has been collected at multiple clinics and hospitals throughout Canada. And the data is transferred initially to a coordinating site associated with the University of Calgary. From the perspective of this workflow, the data originates here at this coordinating site, which transfers the data to the University of Calgary VM, from which all the local workflow tasks are going to execute. And these tasks complete 4 primary objectives. The first is data validation. That is where the data is checked for the expected form, contents, existence in an inventory. And the second is to inventory that data to register the progress of the workflow at different stages. And the third is data archival, where backups of valid data sets are backed up to a different separate file system. And lastly, the data is then distributed to the appropriate sites who are going to do the processing later on. So after the first 3 steps are complete, the validation, the inventory, and the archival, the appropriate data is then shared to the different sites. Each of these sites then independently on their own does some processing on the data to then for their portion, and then is then shared. They then reshare that data right back to the University of Calgary. Some of the derived data is to be processed again at a different site. So before the data is then shared for further processing, the received data then goes through validation, inventorying, and archival yet again. Once the process data of this new data is done, the data is then reshared back to the University of Calgary. So the data that is being passed back and forth between the different sites are continually collected at the very beginning of this whole workflow for a variety of reasons, right? There's different types of scans that a patient might have, initial baseline, 1-year follow-up, and so on. And there's distributed nature of when a patient might actually go into receive their scans. So as such, the workflow needs to operate continually over the multi-year study. And however, the data that's collected is actually not terribly large. It's small enough such that batch processing once a week is sufficient. So once all the processing and the sharing is being complete, the combined data set will be used for 2 main purposes. The first is that all the collaborators will use their their expertise to study the disease that's the focus of this project. And secondly, the data will be published at a FAIR repository to allow for further open source research. So that's a high-level background behind the workflow. So now I'll jump a little bit more into the details of it itself and where Globus fits in. The workflow has been written in Apache Airflow, and Globus is used primarily for the data transfers between the different sites. The workflow consists of 2 main stages, a pre-processing stage followed by a transfer stage. And the pre-processing stage can be further split into 2 parallel sections where the data either originates from the source, the coordinating site, or the collaborating sites for where the further processing happens. Both sections of the pre-processing stage consist of validation, archival, and inventorying. And then the transferring includes distribution, that's the sharing using Globus to different sites with inventorying of those successful transfers. Each of these stages for the transferring portion consists of multiple subtasks where the data sharing sub-workflows are parallelized on a per site basis. The first place where Globus fits into this workflow is during data collection. Derived data is received from a collaborating site using a Globus transfer that is being initiated by a site onto a collection at the University of Calgary. Data collection, whether it comes from the coordinating site or a collaborating site, goes through the same general processes or steps. First, we do data validation. Second, we do notification, where we say the status of the received files, whether it's correct or incorrect data contents, whether it's a repeat series, whether we've been expecting this file or not. And then in parallel, we do archiving and the sorting. And the sorting essentially just takes the files and puts it into the correct location, Globus collection, that's going to be used as a source for the Globus transferred to the site later on. The folders at the end of the data collection stage then become the source locations for the transfers during the data sharing stage. And there are a couple tasks that we do here. First is we check the endpoints to make sure that they're accessible. Then we trigger a Globus flow using Python SDK. And the flow contains two portions. First is the transfer from the University of Calgary to the site. And then we delete the data that's on the source portion of the transfer. And we can delete because we've already archived the data previously, so there's no loss of data in any way. Once the flow completes, we create a transfer list of all the successful files that were transferred. We update an inventory of those successful files, and we send an email notifying what was successfully transferred. One feature I'd like to request, and I've talked to a few people here, and I've already opened the ticket, but I have a microphone, so I'm going to say it anyways, is that I initially looked at putting the status notification in the Globus flow, but I want to include the transfers, the successful transfers from the transfer stage in the email notification. So querying what has been done previously in the flow was not possible. I think it's possible, but something I'd just like to request and something to say here. So this has been a bit of a quick tour going through a workflow using Globus for the transfers. I'd like to acknowledge my collaborators at CPAC and the Research Data Flow Services team at the University of Calgary. So thank you very much.
Great, thank you, David. So David was one of our premier users, one of our first users of Flows, really kind of out in the wild. So you can thank him for part of the development too. Thank you. Okay, up next is Swapnil Bhatkar. Swapnil, there he is. I saw him earlier, so I knew he was here. Swapnil's from NREL, and he is a cloud engineer at NREL, the National Renewable Energy Laboratory, and he's going to talk about event-driven transfers in a hybrid and multi-cloud environment.
Good morning, everyone. Thank you for joining me today. I'm Swapnil Bhatkar. I'm a cloud engineer at the National Renewable Energy Lab for the US Department of Energy. So I build, deploy, and support the research computing infrastructure at DOE. And so you can say, I make sure that the clouds empowers the wind of change that are required in the renewable energy landscape. And today I'm really excited to talk about event-driven transfers in a hybrid or multi-cloud environment. So in a nutshell, event-driven transfers are automated data transfers that are triggered by specific events. And that helps you to streamline your data management in a very complex environment. So in this session, we will explore how you can efficiently transfer your data across various cloud platforms and even to your on-prem systems using Globus. So together, let's shed some light, preferably from solar panels, on how you can build event-driven architectures and implement an end-to-end data transfer workflow using a combination of different cloud components. And this is happening without using the console itself. So everything is done programmatically. And I can show you how that works. Okay. So this will be my agenda for today. It's a short agenda. I'll introduce who we are and what we do. Then I'll discuss some of the common challenges that are associated with high-speed data transfers to the cloud. And then I will deep dive into the event-driven architecture years and highlight some of the important components that are required to build like a highly scalable data transfer service in a multi-cloud environment. So at the lab, we are immensely proud in the range of services we offer to the researchers, the scientists, and the developers. So we want to empower them with the tools and resources that are required for cutting-edge research. So some of the services we provide are data analysis and visualization for researchers so that they can get some hidden insights about their data and make most out of the data. So we also provide large-scale compute modeling and HPC services for computationally demanding tasks and simulations. And we also support AI, IoT and ML projects. So the researchers, they have the ability to either run pre-trained models or even deploy their custom models in the cloud. That's our latest supercomputer, Kestrel. So it expands NREL's supercomputing capacity up to 44 petaflops. So this thing will be completely operational within the next couple of months. And we intend to store at least 100 petabytes of data across all the file systems. So I'm really excited to try this out. And then today we also support all three major cloud vendors today, like Amazon, GCP, and Azure. So we want to leverage the unique capabilities that each one of this cloud vendor provides, and it helps us to provide tailored solutions based on the unique needs of every project. Now I'll discuss some of the challenges and also briefly touch on the alternate data transfer methods that researchers at NREL are using today. So ideally, when you are transferring data to the cloud, you will be most likely using the cloud provider's object storage APIs. And that could be your S3 APIs, your G-Cloud clients, or even your Azure SDKs. But most of these operations are single-threaded. So let's say if you want to start multiple concurrent transfers, then you have to instantiate multiple client sessions, let's say using Bo2.3. So this creates like an additional overhead on the network, and it can create a congestion, like a significant congestion there. And in addition to this, you have to write some utility scripts for monitoring your data transfers. And this process can be very time consuming if you're dealing with a large amount of data sets there. And then there are some third-party open sourced options like S3 command or S5 command, which are written in Go programming language, and they take advantages of the Go's built-in concurrency module. I preferably like this, but sometimes they use all the CPU nodes if you don't specify those worker flags. And I've been hearing a lot of complaints from sysadmins that they sometimes congest the overall compute nodes, and if you are running any other processes on those compute nodes, so the transfer job hangs. So these transfers are highly unreliable, so you have to start all over again. And then there are some managed transfer services that are being provided by public cloud here. So AWS has Data Sync, Google has Storage Transfer Service, and Azure has Data Factory. I would say these solutions, they are expensive than Globus because they not only charge you for the storage, they also charge you for the amount of bytes that are being transferred there, which in my opinion should be completely free. And then they have this pay-as-you-go pricing model, which is really not ideal for your HPC and any research computing workloads, because you will end up paying 100 times more than what you currently pay for your annual Globus subscription. Okay, now let's deep dive into the architecture. So to solve some of the challenges I just discussed, we built an event-driven architecture for transferring data from our on-prem clusters to both AWS and GCP. So on my left-hand side, we have our NREL data center, and on my right-hand side, we have our AWS cloud environment. So in the data center, we have our HPC clusters, and along with that, we have like a few Globus transfer nodes, which are like in a separate DMZ. Now, when a researcher runs a complex simulation job, let's say to predict energy efficiency on one of our compute nodes, so it generates an output.json file. So this JSON file is being used to invoke AWS Lambda function, and it contains all the important metadata such as your source and directory paths, your S3 bucket names, your prefix names, and other important metadata. So this Lambda function with a Python runtime, it creates like a new Globus transfer job, and then it sends the data from on-prem to the researcher's S3 bucket. Once the data lands in S3, it detects those files with specific HTTP uploads, and then it triggers an event bridge rule that is being used to invoke another Lambda functions. And this event bridge rule we have written, it detects those news file in S3, and then what it does is it looks for some specific patterns that we have written. Like, for example, if you just want to include your CSV files or Parquet files, it will detect those files. And just to give context here, Event Bridge is an AWS service that stores and processes millions of events, and then it routes it to any other AWS service or even to your custom applications that has like an HTTP endpoint. And this Lambda function is where the actual processing happens. So this initiates a connection with Amazon Athena, which is again like another serverless analytical service, which is being used to query data directly from S3. And you can use standard SQL or even Python. Now, one of the challenge here is Lambda timeouts. So the maximum timeout period for AWS Lambda is 15 minutes. So we have set content filtering on the event bridge rules we have written. So it invokes multiple Lambda functions in parallel, and then each one of these Lambda functions, they start processing the data, and then there's a final Lambda function that aggregates all that data and sends it to the researcher's result bucket, which we also called as the output bucket. And all of this happens in real time. Now, again, once the data lands in the output bucket, using the same event bridge rule that we discussed earlier, it invokes another Lambda function, which now copies the data from the output bucket back to our on-prem file systems using Globus. And all of this happens in real time. Now, the data transfer mechanism for Google Cloud Storage is also similar. We also use the connectors for GCP. But here, instead of Lambda, we use Cloud Functions. Instead of Event Bridge, we use PubSub topics. And instead of Athena, we use BigQuery. In my opinion, again, BigQuery is a far more powerful solution than any other options there, because it also let you simultaneously process your ML workloads, which I think is a great addition, especially nowadays. Okay, so assuming that the researcher is transferring like a 1 terabyte of data, so this entire round trip process will take less than an hour. That includes the data transfer as well as the processing. And the cost of this setup, especially the cloud infrastructure, is less than like $100 per month, because for the most part, we are using all those serverless components and you don't have to provision any VMs in your account. And this entire infrastructure, especially the cloud infrastructure, is built using Terraform, which is like an infrastructure as code tool for provisioning cloud resources. And yesterday, Rachna talked about repeatable research. So that's our idea of repeatable research. So what we do is we have written some reusable Terraform modules, and then we distribute it across the lab so that project B can use the same components that project A used, but with their job parameters.
Okay, thanks. Thank you very much.
Yep, thanks. Thank you.
Yeah, thanks. Next, Jason Zarowski. Jason is from the Energy Science, the ESNet Energy Science Network. He's a science engagement engineer, and he's going to be talking about the faster data DTN framework.
Thank you all. I'm also representing my colleagues Eli Dart and Ken Miller in this talk. They could not be here this week. I've given this talk a bunch of times to Globus, so hopefully some of you may remember this. If not, a little bit of a refresher here. And something that's motivated by what Ian and Dan said yesterday is that networks really are an essential part of data-intensive science. I don't think that's a shocking statement that anybody should be surprised about. And what our group within ESNet has been doing for over 15 years now is basically trying to get people to understand that, yeah, that's a critical thing that you need to be worried about. And certainly tools like Globus are a part of that, but there's a whole other systemic bit of things that you need to worry about. And that includes the servers and the networks and the security infrastructure and everything that rides on top of it. So we spend a lot of time trying to work with the end scientists to get them to use Globus and things like that, of course, but also working with the different IT groups to try to manage and fix that component of the workflow to make our lives all a little bit easier. And to that end, we've been doing a couple of these various exercises within the communities. Previously, it was called the Data Movement Exhibition. Now it's called the Faster Data DTN Framework. But the goal here is that we want to revisit this with a lot of the large facilities and the small ones, and try to get them to understand that by adopting a couple of simple approaches, both to your network architecture as well as your security profile, and your overall workflow approach, you can get a lot better performance out of trying to do your data movement activities. To that end, there's a whole bunch of things that are involved in it. I'm not going to be able to go into any minute detail here within the lightning talk, but certainly grab me sometime after. It is systemic. It requires thinking about your network architecture. It requires thinking about test and measurement infrastructure. It requires thinking a little bit about hardware design, as well as using tools like Globus. What we had wanted to do is try to get everybody with a 10 gig connected DTN capable of hitting a very, very simple baseline of about a terabyte an hour, which really is about 2.2 gigabits per second in terms of disk per disk performance. And that's pretty achievable with current hardware today. We're going to be trying to get a little bit better with some of our major facilities, though. And because I'm contractually obligated, I have to stick this in every single slide deck I ever give. But here's the Science DMZ design pattern. A lot of facilities have implemented this, including many of you who are sitting here today. So this should not be a shocker for anybody as well. This is kind of what we're trying to get in terms of people's upgrading their performance expectations. And it is a bit of an eye chart. It's a little bit hard to read here. But this is the absolute baseline on the left-hand side there in yellow, which is about 1/6 of what we're calling petascale. And you should be able to do any of those sort of 3 columns with a 10 gig capable DTN today. Off the shelf, you should easily hit the first level. Some tuning is required to hit the next couple there. What we're looking to get with our DOE facilities and large NSF facilities is into that petascale territory where we're capable of moving at least a petabyte or so in a weekly basis or on a daily basis. But to do that, you really do need to have stuff that's tuned and working well in high performance networks. And sort of the ultimate stretch goal that we want to reach here is with the major facilities, which would be HPC centers, it would be instrumentation facilities like APS and ALS. We want to be able to get to the point where we can easily and predictably move 2 petabytes of data in a single day. And to do that, we need to have 200 gigabit per second or so performance. And we're seeing close to this right now. Ian was mentioning the ESGF workflow that was moving data from Argonne to Oakridge, and that heated up our network, and we were able to deal with that. And we want to see that be a regular and achievable thing for the large facilities. For the user and collaboration sites, which are your universities and laboratories, 4 petabytes a week is the ultimate stretch goal here, which is about 50 gigabits per second sustained performance, which we should be able to do, but it's going to require some upgrades to get there. And this is an old and dated slide, but this is a couple of years ago, we started and took some measurements between everybody, and we were not quite getting the performance that we thought that we were going to get. After just even a couple of weeks of work, we were able to get 4 to 10 times better performance with everything. We've just started doing the baselining again with all of the major computing centers, and we're going to be looking for sort of anybody who wants to participate in this effort. So we're getting the baselines now, and we hope to have some better numbers next year when we report out again. So in terms of next steps, if anybody is interested in participating in this, please certainly grab me. We will be reaching out to all the labs and facilities and some of the major universities and research networks to participate in this. One of our motivations is that LHC data is going to be increasing by oodles of volumes in the next couple of years as they hit their high luminosity targets. So as a result of that, we're going to be seeing lots of network upgrades, and anytime that you upgrade something, you probably are going to break it. So as a result of that, we want to be able to test it, measure it, make sure that it's working as best as we possibly can. Ken is the lead on this. You can hit him at ken@es.net or the EPIC list or me directly, and we'll certainly work with anybody who's interested in working with us. Any questions?
Because you can never have too much APS. We're gonna we got our last APS talk. Can you tell we like those guys? So John Hammonds is a principal application developer at the APS, and he's going to talk about integration of GCS v5.
So, hi, my name is John Hammonds, and I'm, of course, with the APS at Argonne. I didn't do all of this work by myself, so I have a list of collaborators listed here, so credit them with a lot of the work. So in case you haven't heard about the APS, this meeting yet, the APS is a large experimental facility for doing X-ray science at Argonne National Laboratory. We have approximately 68 beam lines running simultaneously, all taking data. And our use of Globus is in association with our data management system. And that is set up to move data from the data collection at the beam line to a central storage, provide access to our remote users, give them access to the data and only the data they're supposed to be able to see, provide some mechanisms to create workflows and data processing and so forth. This particular talk, I'm really going to concentrate on GCS and our transition from GCS4 to GCS5. Hannah Paraga talked yesterday on more of our use of the other tools for Globus compute and so forth yesterday. So I'd refer you to her talk for that. So we've been using Globus at the APS for something on the order of 10 years, moved tons of data back and forth, shared data with all the users and all of that good stuff. But as the Globus folks want us to do, we want to move to Globus to GCS5 more to get out the new features and to free them up for new developments. So with GCS4, we had created one collection and we shared data to all of our different beam lines with that one Globus connection. As we're moving to GCS5, we're looking to create one mapped collection for each of our beamline stations. Part of the reasoning there is if for some reason we run into some bottlenecks and so forth, we need to split things up into different endpoints. It frees us up to do that. The way we handle users is that on an experiment by experiment basis, we create a group, an LDAP, assign permissions to that directory, and then as users browse the Globus, and they only have access to the data where they're part of that experiment. And that's being done on both GCS4 and GCS5, where we're using that LDAP to give a lot of the permissions. With GCS4, when we implemented this originally, we had user accounts that were based off of our web accounts that we use for things like submitting proposals, experiment safety forms and things like that. And the users would authenticate to the GCS4 collection through a My Proxy page, which means that they had to separately log into Globus and then authenticate to the collection. As we're moving to GCS5, we're able to make use of the mapped identities as Greg talked about yesterday. All of our users now have a ANL domain account. That was actually done sort of independent of this, but it was a really good advantage for this, that we were able to leverage that. So now they can log in to Globus, say with user@anl.gov, and they'd be able to see their data. But more ideally, they would actually log in with their own home identity and link their ANL identity to that. And then that is what gives them the permissions to see the files. When we were with GCS4, We really could only share data with users that were registered in our user database and part of our system. And that was a little bit of a problem for some people. Not everybody was a part of a registered experiment. Some people wanted to share to other members of their groups. With the guest collections, we now can provide that level of access. We can just add them to a Globus group that is part of a guest collection, and then those users would have access to that data as well. So they, our users can share with their collaborators without them being a registered user at the APS. Another feature that came along was this HTTP download that was demonstrated. Not all of our users have such an easy time installing the Globus Personal Connect, just due to restrictions from their home institution on installing software. So that's an advantage we hope to pick up there. So how did we implement this? It's a large facility, so we want to do this in a bit of organized way. It's part of our data management system. So, a lot of the terms in the green boxes you recognize from Globus, endpoints, collections, and so forth. But also we have records of these things in our data management system in our database. And I've tried to list here, what we keep track of. The blue items here are ones that are more of one-off creations. And for those, we use the Globus Connect server command to just go ahead and create the endpoint, create our base level beamline map collections. The items in green are ones where we're going to be dealing with a lot more day to day. Our beamline folks are going to need to make modification to these, create these on the fly as they run new experiments, create new experiments. So for those, we're using Globus SDK and integrating this in with our DM system. They're just added as part of our services. That allows us to have command line interfaces, hook them to our GUIs and so forth. We would have one beamline map collection per station. We'd have a guest collection possibly for every single experiment. For sharing the data, that's not absolutely necessary. People that are in our database could get access through the map collection. But as I said, to share outside, the guest collections are helpful. And also for some of the other features of Globus, the guest collections are useful. We will have a station manager group for each station that will allow us to give our beamline staff the ability to manage some of the things for the experiment level on their own without coming to us to help manage that. It will allow them to do some of the things through the web GUI and so forth, or even through our commands. And then we'd have a guest collection for possibly every experiment. Right now in our database, we have something on the order of 9,000 experiments. And that number is just going to keep growing. So we will have a lot of guest collections coming up. And then there would be a group associated with that experiment as well. And that's where we would add all of our users attached to that experiment, possibly the people who are not part of the APS system, we would allow adding in there. And just so I don't miss it and I get caught up on time, I'm going to jump to the middle of this. The Globus support team has been very helpful with this. And I've listed a few people, Dan, Stephen, Gigi. They've been able to take the questions, at least I've asked, where I really had no idea what I was talking about, and give me some really good feedback. In a lot of cases, a number of examples and so forth. So the user mapping, I think, has really simplified things. The people are just going to log in, they're going to be able to see their data. There's no dual login anymore. Once they get their account linked and answer all those permission questions the first time around. The guest collections are giving us a way to share experiment data with people who are not part of the APS system. The HTTP download button, we've had a number of people asking for ever since that button appeared, and we've been trying to get it out there. We started working on this before the Globus SDK was fully equipped for GCS5. My first question was, how do I do this for the map collections, the guest collections, so forth? It wasn't there yet, so that was fun. And things with GCS5 were not totally backwards compatible with GCS4. but we were able to set up an independent system. We're looking at a GPFS disk store. So we were able to have both of them pointing at the same disk. I don't know if my actual statement there is quite true about backwards compatibility, because Rashana said that there were some migration tools, but it may not have worked really well with our user mapping. And as with any project, documentation could always be better, but I think it's really improving. And in many, many, many examples, especially in the Globus SDK, have been added to the system.
Great, thank you.
Thank
You, John. Thanks.
Thank you.
Yeah, appreciate it. Jason Banfelder from hang on. Yeah, Jason Banfelder from Rockefeller University, right? He's the director of HPC systems. He's going to talk a little bit about Globus flows. Again, another one of our premier first users of flows.
All right, thanks for having me. So Rajana mentioned yesterday that about 95% of Globus users use the web interface only and get a lot of mileage out of that. But we're seeing here today that there's a host of other things that are available, but that require maybe some deeper knowledge and some more technical usage. And I found when I was making that transition, and I'm still very much in the process of doing that, that there's about 5 or 6 different things that you need to learn all at once to be able to be productive. So what I wanted to share with you today was just sort of an outline of the first few steps that you might take to be able to make that transition. And I'm sort of taking an agile approach here. So this is my journey for the first useful thing that I could deliver to my customers. It's by no means the best way or a complete way to achieve the goals, but that was the philosophy. So with that, Rockefeller University, obligate nice picture of our campus on the Upper East Side of New York City. I run the high performance computing and scientific computing group. We basically help researchers do scientific computing. We run a cluster not quite so big as some of the others that you've seen today, but we're a total of 85 labs in the institution, and this mostly meets our needs. So I have 3 motivating projects. This is the journey that I want to take, and this is really again more for learning than at least for now in the spirit of Agile, right? So the first project is very simple. I have a single sequencer that is owned by a single lab, and I need to get data off that sequencer onto our high performance computing cluster so that researchers can analyze that. We have in between what we call an ingestion server. This machine is physically attached to the sequencer. That orange bar does not go through the campus network, and that protects the data collection from any idiosyncrasies of the campus network. And we'd like to automate this process of transferring data from ingestion to the HPC cluster. The second, that's really just a prelude. You could do that with an rsync and a cron job. But looking forward, the challenges that we're going to be facing in the future are our cryo-EM facility has 2 cryoses in Antarctica producing about 100 terabytes of raw data a month. This is going to multiple labs, so really dovetails nicely with Globus's ability to transfer data correctly. You notice that we have another sequencing facility that has a NovaSeq, and you see the permissions that are used to effect the transfer. That's not good. We don't want to make world writable directories. We want to get it right. So that's definitely going to be a challenge for our cryo-EM facility. And then lastly, we have a bioimaging resource facility. This is a collection of a Noah's Ark of light microscopes that also we want to move data into an Omero instance that we're standing up now. And the really interesting thing about this one is that about 20% of the customer base of this core facility is extramural, right? It's data that has to go outside the campus. And that's really where we love Globus because we don't have to talk to lawyers. Right now, this is a SneakerNet application where people actually come in and bring a thumb drive to collect their data. So we're hoping to, with our Omero install, make the data available in a modern way. Okay, so I'm going to just talk about how I achieved the first project and some gotchas along the way. And I want to thank Rashana for sort of guiding me through this and giving me the hints that I needed to get it working quickly. So first is if you're trying to learn how to use flows, and we decided to use flows to do the transfers, use guest collections for everything. That limits blast radius, gives you more fine-grained permissions. Also, you'll find that you'll need fewer consents with Globus. If you're using a map collection, you'll keep having to renew consents with guest collections. You hopefully won't need to do that. So just start with guest collections and use them throughout, and a whole class of problems go away. Tutorials that Globus has, they actually have some tutorial endpoints. I prefer to know what I'm working with from the beginning. So I just fired up GCP on my laptop, created 2 guest collections, and that was my development environment. Again, also very risk-free, right? I mean, my laptop is essentially sacrificial if it needs to be. Everything's backed up in the cloud, right? Okay. Second thing was actually finding how to get started with flows was a bit of a challenge. It turns out that at least the documentation that resonated with me was actually in the API section of the documentation on the website. I found that kind of surprising. Usually the API is where you get the nitty gritty, you know, this is the function signatures of the REST API calls and so on. But this is where it actually has, like, you know, very gentle introduction of go to the website, click on this and so on. That it wasn't the obvious place for me, but this is where I needed to start. So you go to Globus Flows, go to the API documentation. There's a very nice tutorial that starts with using the web interface. I will also say another thing that I found surprising was when you click on the little flows icon, it shows you a lot of flows, and there's a lot of cruft from other tutorials and other people's stuff and so on. So just focus on the things that are provided by Globus and have a little Globus icon next to it. The rest is probably not what you're going to want, at least in a learning phase. So you can click on the buttons. It's pretty obvious how to run a demo flow. The Globus move, copy, and delete is a good one to start with. So you'll run that through the web GUI, following those instructions. It will work. Again, this is just moving files on my laptop, so I can type ls and see what's going on under the hood and so on. So one of the things that you'll find is that after your flow runs, you can go and see an event log, so you'll see that the flow worked. And one of the nice things in there is you'll find a JSON stanza that is the input in JSON format to the flow. This is basically what you typed in the form that you filled out before you clicked go in JSON format, and you're going to want that. So copy paste that, and you don't actually want the whole thing, you just want the part I highlighted in blue here. Stick that in a file, and now you're going to run the flow from the command line instead of from the GUI, since you ultimately want to automate things. So you can basically just refer to that file that you created, run the Globus automate flow run command, and give it the flow ID, which you also get from the web interface. Okay, next is you probably want your own flow, not exactly the one that Globus created. So you'll again go to the web interface. You can copy the flow definition, which is a JSON file. So you will need to learn to love JSON if you're going to work with Globus flows as it comes now. You will need to do some reading. Globus flows is based on the Amazon State language spec, so you'll want to read at least the first half of that, and then some more documentation on the website. You can then go in and modify the Globus flow that was provided. I actually studied it by reading that JSON file line by line. There is actually a tool this can generate the diagram automatically in dot format, but I use JSON-CAD to make the diagram. You can modify that. In this case, I actually didn't want to do the delete part at the end, so I just took out 2 states and rewired and so on. Automate with a single, deploy the flow with a single command as shown here, and then you can run it using the same Globus automate flow with your ID and your input. Then production deployment. Basically, so that basically allowed me to transfer a directory from the ingestion machine to the thing, to the HPC, again, using guest collections on both sides. Guest collection for the target should be owned by the person you want to receive the data. And then basically I just, to start, just use a cron script running on that ingestion machine to look for a specific set of files that I know exist when an Illumina sequencer finishes a run. There's 3 files that are listed here. And I'll also point out that that is still a little flaky in Illumina land. So we actually coded that those files have to be there and not changed for 15 minutes. Because sometimes, even though those files get dropped down, the sequencer is not quite done yet. So we just put in a 15-minute buffer. And lastly, I cheated because I didn't want to get into the SDK yet. So my Python code actually just shells out the same Globus automate flow run command I know I can do better, but again, this was enough for me to deliver something that actually worked. And since that's been running for now, I don't know, several weeks, and that actually worked the first time, which is astonishing for a technical project. So with that, thank you.
Next, a longtime friend of Globus, Mitch Griffith from Oakridge National Laboratory. He is the archival storage software developer, and he's going to talk to you a little bit about his workflow, archival workflow improvements.
Okay, so I'm Mitch Griffith from Oakridge National Laboratory, and what we have is a product called Constellation. It was brought into production about 2015. I don't have a screenshot of the website because it looks like it was developed in 1994. And we do have updates to it. And we have people who have been hired to make it look a little bit better, be a little bit more user-friendly. And we're looking at redoing the process itself. So the main point behind this is it's a way to get data, create DOIs. We are integrated with OSTI to mint these DOIs. The important thing here to realize is this is all open data. We don't have any proprietary or sensitive information on here at all. We're allowed to share that data with the entire world once it's actually approved. There is an actual human in the process whenever we go to approve these DOIs before they are created. So it does take a little bit of time in order to actually move all of our data over there, get someone to look at it and go, yes, this is okay, or, ooh, you actually still have PII information in this DOI, so we're gonna have to remove that before we can create it, that sort of information. And one of the big advantages of what we've done with Constellation is we do have Globus in use for all of the data transfers right now. We are a GCS version 4, so we are hoping to upgrade by the end of this year, last I'd heard. But one of the big advantages that we're hoping to get from GCS 5 is the HTTPS upload and download. So those are some of the advantages that we're hoping to take away from this. One of the things that we did in the DOI archive process is that we have a data movement agent. And for that, we have our DOI landing page. In order to make sure that what we actually received stays what it is in our archival system, we try to keep a list of all of the files and file sizes that were transferred in this particular DOI. Right now, for the Globus SDK, we could only get that information from an operation LS. And trying to do that recursively, we did just a naive attempt with that. And for the majority, like 90–95% of the DOIs that we get, that works perfectly fine because just doing it serially, it happens and it does not take that long. The problem was that we started getting a lot of, well, we had a couple of DOIs come in that had several hundreds of thousands of directories in there, and trying to do that serially with each REST call, it was taking a long time. And we were trying to think of what can we do? Can we change our requirements to where do we really need the file size? And use the task successful transfers API call, or do we actually need them just to help verify that what we actually receive stays what it is in the archival system? But if you'll look at this, so the improvements that we did, the serial operation LS call on about 480 to 83,000 files in 96,000 directories took 8.5 hours to complete on ours. And our time was affected a little bit by the storage backend, so it took a little bit of time to retrieve those. Listing in another test where we tried to get rid of the operation LS call, we're using task successful transfers, and it took about 1.3 hours to list a total of 2.5 million files. And that was a lot more, that had even more directories in it. I can't remember the exact amount, and I should have put it on here. I apologize about that, but we're looking at about 250,000 directories where we were able to greatly increase that. So also, whenever we're using the task successful transfers, We're using the default limit of 100 for the page size. So whenever you're retrieving the list of files that were transferred, it's grabbing it 100 at a time from each call. We're hoping to increase that to the maximum of 1,000, I believe, and increasing that a little bit more. So those are the improvements that we made in our Constellation front end and how we're archiving our data. And I was just kind of curious, one of the things that we're hoping to get out of here is just see how other sites are doing whenever they are archiving data, if they're just trusting the archive to make sure that everything stays where it is, or do they also have requirements where they have to save which files are in there and any kind of MD5 or file size information associated with that. So that's it.
Great. Thank you, Mitch. Thanks for bringing us home there.
Hi, everybody. Hi, everybody. How are you? I use my radio voice. Everyone's like, you have a low voice. It's good for the radio. I hope you enjoyed your break. We decided to push this to after the break. So I'm going to make this quick and a lightning talk along with all the others. So I'm from AWS, along with Rick Friedman. We have the same last name. Not sure why that is. We're probably related in some way. We're part of the research team at AWS. And what we wanted to do at this little short segment, first of all, thank you all for coming. We're glad that we were able to sponsor the conference this year. I've been trying to get AWS to do this for a while. We've both been in research a long time. Rick has been on the vendor side. I've been on the academic side. I was at UCLA for 30 years before I came to AWS. And what I really wanted to talk about is what AWS, not explain what the cloud is. You all know what the cloud is. You all know, you've probably all heard of AWS. And if you haven't, you can come ask us and we'll tell you about it later. So I don't want to do that. What I wanted to say, first, I want to make a plug for the S3 connector for Globus, of course. And if you're not using it, you should come talk to us. If you are using it, you should come talk to us. I think we want people to know more about it and what you can do with it. I used it in my previous life. I'm particularly excited about the flows and the compute component of this and how you can leverage the cloud for that. What I really wanted to say is, this is the kind of crowd, I don't have to explain the cloud. I don't have to explain, how you can use the cloud in very different ways than we traditionally do on-prem computing. And we're not here, the research team is not here to tell anyone you should shut everything down and move it into the cloud tomorrow or on Monday. We want you to figure out ways or think of ways to use the cloud where it makes sense today, both from an operational standpoint, a research standpoint, and then also a financial standpoint, because we get that, we both know, and the rest of our team knows that, it's not always the most cost-efficient way to do things, right? However, what I really wanted to get across today is let me go to the next slide here. So, the value proposition of the cloud, I think, is still pretty compelling. We're not there on some of these pieces compared to some of the ways things are done on-prem today, and we get that. But what I really wanted to communicate to this group is that people like me, people like Rick and others on the research team, we do as much internal advocacy for this community within the company as we do coming out and meeting all of you at your institutions. And I think that's important for you all to understand. We don't communicate this enough, is that Amazon is a gigantic company, right? AWS is a gigantic company. And let's be honest, most of their effort is geared towards commercial customers. Commercial customers, single commercial customers are probably bigger than everything all of us doing put together. All the data we talk about, all of that is, to some of the S3 team or EC2 team is peanuts. So we're really trying to say, if AWS thinks research is important, which Rick and I are being told that it is, we say, okay, then we need to put our money and our engineering and all that resources, where our mouth is. And we're trying to do that all the time. So we just want to make sure that you understand that there is a research group at AWS. that all of us come from either academia or the vendor side. In fact, most of us come from academia, either individual researchers or institutional level people or vendor folks who've been in the business a long time. And one of the things I wanted to demonstrate this shift is we've spent a lot of time trying to convince our peers at AWS that research computing is not just HPC. There's this kind of mindset that research computing just means clusters, you know, whether that's an on-prem cluster or doing a cluster in the cloud, and that's it. And anyone who's been in this business for any, you know, we've been mostly hearing about workflows and other kinds of things that are people are doing this morning. It's more complicated than that. And I'm using this as an example to show you how we've been able to convince the company to pay attention to this. And I'm going to do that by showing you a product that we just released recently that makes using the cloud for research simple. Now, this is not for people running big clusters. This is for kind of long tail folks. But the point is we're able to articulate internally in the company that this is a problem that people have. You know, the metaphor I like to use for the cloud is like Legos, except it's not the Lego set, right? It's just the Legos. And you can build whatever you want in the cloud. But that's really hard. When you go to a researcher and say, well, cloud is good. Maybe the cloud is good for this project. And you have to spend 6 months learning how to use the cloud, kind of a dead end conversation. And one of the things that we've been asked is how can we make it simpler for people to use? And I know there's a lot of open source projects and things that are out there. We even have some that we've put out. And what we did is we created something called Lightsail for Research, where we really, for the first time, tried to address many of the concerns and worries that people have about using the cloud, particularly non-technical users. And it's called Lightsail for Research. And what I want to say is this is the first time, this is a project that we initiated. This almost never happens at AWS. The service teams come up with new services and they keep, anyone who follows AWS, right, we have a fire hose of new services every day. This is something that very high up people at Amazon we pitched it to them and they said, we love this. And they threw 6 Amazon engineers at this. So you can imagine what 6 Amazon engineers cost. And they built this pretty quickly. And what it is it says simple installation process. There's actually nothing to install. This is what happens when marketing looks over your slides. It doesn't require any skills to use it. It's simple to explain. Usually I don't show slides, I just demo the thing and I encourage you to give it a try. The 2 exciting things is the pricing is bundled and it has cost controls built in, which are the 2 things that people complain about the most, other than sometimes they think it's too expensive. Bundled means you know what the cost is ahead of time, and cost controls means it'll shut off when you're not using it. That doesn't happen with EC2. That doesn't happen with normal cloud issues. People are always worried about, you know, I'm leaving a GPU system running over the weekend. And what this is for is these long tail users. I like to say the folks above the waterline in an iceberg metaphor, they're either capable on their own, or this is where research IT and central IT people, infrastructure people are putting most of their limited resources. People bringing in a lot of money, everybody else. So when I was at UCLA, I had to support 14,000 faculty, plus postdocs, plus professional staff. I had a team of 40 people. That's not, which is quite a few, but not enough to handle everybody's needs. That's those folks. And a lot of them needed something that was a little more than what their laptop could provide. And of course, they're very budget conscious. So we want to have very transparent budgeting and transparent cost and spend. We want to show that all the time. So again, just another way of looking at the same thing. You know, there's a limited amount of resources to help researchers on campus or research institution. That's where most of those efforts are properly devoted. But then there's everybody else. So we're getting a lot of requests for, we need something that's self-service. We need you to help us take some of this load off. We don't have good solutions for this. Or we built something and you can have anything you want as long as it's black, kind of a model, which a lot of researchers are like, That's not what I want. I want something that's more capable or more tuned to what I want to do. So when I say this is an actual service, this is built into the console of AWS. This is not a third-party thing. This is not an open source thing. This is literally part of AWS. It shows up in your AWS bill. In fact, when the system is off, it shows up as a different line item. This, you know, I have demo or UCLA here, it's off. It's charged at a different rate. What's neat about this is that this is, I don't need to really show much more of the interface than this, but I think what's really exciting is that like everything else at AWS, it's all API based. So if you don't like this interface, you don't want to use it, or you want to customize the systems that are spun up, just you can just use the API and do it any way you want. So if you want to integrate it into other kinds of services or things that you're doing on-prem, that's very easy to do. Cost control rules, again, these systems were stopped. You can see that I've spent less than $1 on each one of these. I walked away chit-chatting with somebody and the system stopped for me. If I run something, an analysis that runs for 3 or 4 hours and it's done, I don't have to worry about shutting it off. It'll shut off by itself. Now, the last thing that I want to say about this is, well, actually, I could go on, but I'm not going to. I think that this is the real point of showing you this is not, you know, I encourage you to check it out just because it's something we're excited about. But the point is that this is a demonstration, I think, of the company trying to pay attention to what needs are. It's not solving all problems. It's not trying to solve all problems. There's lots of things that I wish this could do that it can't do yet. Maybe it never will. But the point is we have people that are paying attention and listening and are empathetic to the needs and also empathetic to the way that research works, both, again, operationally and financially. So I'm hoping that in the future, we're going to start shifting our ability to work with all of you to do things in a way that everybody, I think, has been asking for. Can't promise that, but we have people like Rick and I that are really trying to push things in that direction. And if you take a few minutes to try this out, if you want, it doesn't cost much, but if you want credits to do it, you can let us know, and that's easy to do. I'd be very happy to hear what you think about it, good, bad, or otherwise. Anyway, I will stop there. So thank you very much. There's my email. Feel free to reach out. And again, I hope you enjoyed the conference and thank you for having us.